All right, so let's quickly go through the key on the exam. Good question. All right. Hey, everybody, we got to settle down. I know you guys are wound up. All right, so for the first problem, we have to identify the number of unique proton signals. There should be 5 unique proton signals. One for here, that lower position. Here, that's 2, 3, and then 4. So we've got 4 proton signals. And then if we go through and we do the next one, all of these methyl groups are the same. So that's 1, then we've got 2, and then we've got 3. So this should be 3 proton signals. If we go through and we do the next one, are these 2 methyl groups on the end the same?
Yes.
Yes.
Yes. Yes.
Yes, they spin around, so they're the same. Did you have a question, JJ?
Why didn't we count the 3 hydrogens from the methyl on the first one?
On this one?
No. Oh, because it's symmetrical?
Yes, this is a short
No, not that
No,
one.
on the left.
First one.
This one?
No, the other one.
On
That's
this one?
because it's symmetrical.
Yeah, because we've got a plane of symmetry going smack down the center of that molecule. Exactly. All right, so if we look at these 2, these are the same because this isopropyl group can spin like a helicopter blade.
Dr. Engel, I mean, I understand that that's symmetrical, but if you continue up, that's not symmetrical because you have a double bond oxygen and an oxygen and a hydrogen.
So let's take a look. If I highlight this bond right here, this blue one, can that rotate?
Yeah.
Yeah. So we have to pay attention to any sort of rotational symmetry as well.
That can rotate because it's got a double bond right there.
So if we look at this, it's a sigma overlap. Sigma overlaps can spin like this. It's not a pi bond. It's not locked into a conformation. So it's a head-on. It can rotate.
They're like connected things. So like because I thought that there was one here, but it's
So think about a sigma head-on overlap. It can spin and rotate. A pi bond, you've got p orbitals sticking up and down. And so that locks it into a conformation. A sigma bond isn't locked into a conformation. All right, so the next one over, we've got 2 methyl groups that we said are equivalent. The next one in is its own unique one, so we're at 2. Then we've got 3. What about these last methyl groups? If we look at this one on the top,
No, sir.
that's cis to an isopropyl group. This other methyl group is cis to a methyl group, so they're different. So we've got 1, 2, 3, 4, 5 different proton signals here. If we look at the next one, we've got unique proton signals here, 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 and here. What about the other benzene ring on the other side?
Symmetrical.
It's symmetrical, right? Because if we look at this molecule and we draw a plane of symmetry, it's the exact same on the left and right. So this one has 4 unique protons. All right, now let's go through and try to identify unique carbons really quickly. I'm going to speed through this, but if you see something that just doesn't make sense to you, raise your hand and we can stop and talk about it. All right, so for this first one on the left, we've got a unique carbon here, 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 and here. So 2, 4, 6. So we've got 6 unique carbons. Over here, all 3 of these methyl group carbons are the same. So that's 1, 2, and then 3. So that has 3 unique carbons. If we go over to the next one, these 2 methyl groups we said are the same. So that's 1, 2, 3, 4, 5, 6, and then 7. So 7 unique carbons. And then the last one, how many do you guys think there are? Go 1, 2, 3, 4, 5, 6, 7. Exactly. All right, so this is going to probably show up on an exam in some way, shape, or form. So make sure that you have this mastered by the time the exam rolls around. All right, now the next one. This was actually a compound I worked with in grad school as a building block. One thing we need to pay attention to are unique sets of protons. This alkyne proton off the end is very unique. Should this be a singlet, doublet, or triplet? Singlet. It should integrate as 1 proton. And it should show up actually around 2 ppm. As if you were within the ballpark, I give you credit for that one. What about these protons on the amine? Would it be a singlet, doublet, or triplet? Singlet. There are no 3-bond neighbors, so I'll say singlet, 2H. And these oftentimes show up around 4 ppm. I give you credit if you were in the ballpark. They show up a little more downfield because they're attached to an aromatic ring, right? All right, now let's look at the next one. So I'll call these HB. This will be HC. What should HC be split as? Singlet. Nope. So it should be a singlet. It should integrate as 1 proton. And where do aromatic peaks show up? 6 to 9 ppm. What about HD down here? How many 3-bond neighbors does it have? 1, so it should be what? Doublet, exactly. So I'm going to draw an arrow to this one. It should be a doublet. It should be 1 proton. It should also be 6 to 9 ppm because it's aromatic, just like HC. What about this proton? Is that the same as HD or different? Different. So we'll call this HE. And this is pretty similar to HD. What should it be split as? Doublet. It should be 1 proton. And it should be 6 to 9 ppm. And let's look at these ones over here. I'll call these HF. What should HF integrate as? Or split as? How many 3-bond neighbors does it have? 3, so it should be split as a quartet. It should be 2H because there are 2 protons, so integrate as 2. And then it should show up right around where? Does anybody remember? Close to 2 ppm. So I'll say approximately 2. And then we've got HG over here. What would HG be split as? Triplet, right? Because it's got 2 3-bond neighbors. So triplet integrates as 3H, and it should probably be around 1 ppm. So as long as you were reasonably close to the shifting values, I give you credit. I'll give you the cheat sheet on the next exam too, but next quarter you won't have access to the cheat sheet anymore because we need to get ready for the ACS final. Yep?
Okay, I know you already explained it, but for the hydrogen bonding to nitrogen, can you explain why that's around 4 ppm?
Because it's attached to an electronegative nitrogen here,
Yeah.
and it's next to an aromatic ring.
How are we supposed to know exactly the numbers out? Because it's not on the chart.
Oftentimes we have to just do a good approximation. There's nothing that can replace experimental data though.
So for that one,
Just treat it as like an oxygen.
Treat it like an oxygen. A nitrogen is fairly similar to a nitrogen in terms of
that's
electronegativity.
what I did, but the range for the oxygen is between 6 to 1. I'm wondering how you
If that oxygen were attached to an aromatic ring, then it would shift it. So we're combining the attachment to an aromatic ring and attachment to an electronegative atom. Yep.
So on the exam, I mean, do you want like us to take more of like an approximate, like approximately 2, or can we give like ranges? Like
You can give a range. As long as you're in the ballpark and you're not off in some bizarre range, I'll give you credit for it. Yeah. No, you can't do 1 to 12. You can't, put the whole spread out there and say it's going to show up somewhere where NMR signals show up, right?
It's in there. I mean, come on.
All right. On the back page of the quiz, everybody, on the back page of the quiz, we had 2 different problems. So depending on your mass to charge ratio, your molecular formula may have been a little bit different. So the first one was an M to Z, so mass to charge ratio of 68. Either way, though, when you go through and do the math, you would say, all right, we've got 4.3% for our maths plus 1 peak, divided by 100% intensity, divided by 1.1, right? Yep, times 100. And this tells you that there's going to be approximately 4 carbons. Right, so regardless of your mass to charge ratio, you should have hopefully been able to get to the fact that there's approximately 4 carbons in this molecule. It was 3.9, but that's very close to 4. It's within the range of error for the instrument. And then we have to fill in the gaps too. So if you had a mass to charge of 68, that meant that you had C4, you had H4, and then O. That would give you the mass to charge ratio. Why isn't there a nitrogen in here?
Because it's not odd.
Because it's not odd, right? If it had a mass to charge ratio of 74, then it changed a little bit. It was C4H8O. So they were slightly different. So you had to kind of fill in the gaps with remaining oxygen or hydrogen atoms. Obviously, there had to be some sort of oxygen in there because we couldn't make a molecule with 20 hydrogen atoms and only 4 carbons. So you have to use some of your problem solving to figure out the molecular formula.
It should be H10.
Oops, C4H10, thank you. Sorry. C4H10O. So those were the 2 different molecular formulas depending on your quiz. And then the next hint I gave you was that the carbon-13 NMR only had 2 signals, which means that the molecule is symmetric or asymmetric. Symmetric, right? If we have 4 carbons and we're only getting 2 signals, that means we have some sort of plane of symmetry. So if we have a mass to charge of 68, and we've got that molecular formula we came up with, the most probable answer would be this one. I gave people credit for a few others. So as long as yours was reasonable and fit the molecular formula, you got credit. And then for the mass to charge ratio of 74, you could have either had diethyl ether. Ooh, here we go. There we go. You could have had diethyl ether, or you could have had tert-butanol. So those were both perfectly reasonable answers. One good trick you can use is always do the HDI. The HDI, or the hydrogen deficiency index, will tell you how many rings or double bonds you have. If you do the one on the left, it has an HDI of 3, and then the one on the right has an HDI of 0. All right. If you do notice any discrepancies with your exam, don't be afraid to bring it by and we can talk about it. I occasionally make mistakes, so bring it to my attention if you think you spotted something that wasn't graded correctly. All right. Yep.
Do you know when our next quiz will be? Because I know it's scheduled for Thursday.
I'll email you guys. Because the schedule's been shifted around, it will be either shorter or next Monday. I've got to figure it out with the schedule. Okay, so let's jump back into chapter 17.
Actually, I think I'm back. You already made those problems work so much.
All right, so yesterday at the end of our quiz, we talked a little bit about conjugation. And we said that conjugation is easily spotted by seeing the alternating single, double sort of configuration. We said if you have 2 double bonds side by side, it's called cumulated, and then it's called isolated if you don't have an alternating double single pattern. In this case, we've got double, single, double. So this isn't conjugated. The one on the far left is, because it's got the correct ratio. Yep.
So for the accumulated, is that just like how, is that one molecule?
Can
you have 2 double bonds next to each other?
There are unique functional groups where you have a carbon-carbon double bond like this, and they're linear, and those are called allenes. We don't run into them very often. We saw an example of it last term.
Okay, but it exists.
It exists, yeah.
Okay.
They're not common, though.
Okay.
And we said that conjugated molecules have this inherent stability because they can delocalize their electrons much more so than a normal alkene or an isolated system where you've got multiple alkenes, but they can't communicate with one another electronically. And we briefly started talking about the orbital overlap for these conjugated systems, and we said that if you're looking at a double bond between these 2 exterior carbons, that these p orbitals can talk to one another, but it's also in resonance where these interior carbons can talk to one another because all of these p orbitals are in line with one another, so electronically they can communicate. And we said because of that, this interior carbon-carbon bond has double bond-like character. It's a little bit harder to rotate than a normal sigma bond, and we said in particular it takes about 15 kilojoules per mole to actually rotate that single bond. And so it's not truly a single bond, it's in between a single bond and a double bond a little bit. So let's get an idea of what's going on at the molecular orbital picture. And I pulled these out of the book because I'm a terrible drawer. And so let's take a look at the example we had in our notebook. So I'm going to emit hydrogens for clarity. And we said before, we've got these p orbitals sticking up and down. And these really want to communicate with one another. But one thing we oftentimes overlook with p orbitals is that is the top lobe the exact same as the bottom lobe?
Yes.
Yes. No. I don't. Yeah. They're like half and half.
It's kind of a yes and no.
It's a sandwich.
Right, so if we look at the carbon, there's a node, right, where that carbon atom is. The top lobe is actually in a different phase than the bottom lobe, right? So they're not perfectly the same, they actually have different phases. The electron can be in either phase, but in order for that overlap to occur, both p orbitals need to be in the same phase. So let's take a look at this one. This is 1,3-butadiene. I'm going to move this molecular orbital map up. So it's okay if you don't want to copy this down. I know it's pretty difficult to copy, but if you look at the bottom one, this is exactly what I've drawn. And the p orbitals hybridize together. And in this case, the top lobe is all in the same phase as the bottom lobe, right? So this is a very, very stable molecule. It's got the lowest energy out of all of the possible orbital configurations. If we go up one, we can say, well, what if we include a phase change in between the center carbon-carbon bond? Now we've got different phases on the left side and right side, but we still got overlap between the two adjacent carbons. So this is still relatively stable. And then theoretically we can say, well, what if we keep on taking this further? This one we had one node. What if we have two nodes between there? So now we've got an interior double bond-like configuration. So these two p orbitals are sharing, the outer p orbitals are now just on their own. And then we can even go up to 3 nodes where we can say, well, theoretically, these could all just be separate p orbitals with their own unique phase. The reality is we only have 4 electrons in here. So these like to fill up from lowest energy to highest energy, so we'll take these lower 2. But if we apply energy through the form of light or some sort of heat, we can actually take one of these electrons and raise it up to one of the higher energy levels. And we'll talk a little bit more about reactions where that's very common. Yep.
So are these continuously changing between phases, or do you have to apply energy to change the phase?
It's just like the off-bow principle where it says we fill up the lower energy orbitals and then we go higher and higher and higher, and then there are even theoretical empty orbitals above that. Same principle, but now we're looking at orbital mixing of adjacent p orbitals next to each other. We're not going to go too far into this. If you go on and take advanced chemistry courses, you'll cover this quite a bit more. All right, let's see another system that takes this to even the next level. This one's pretty crazy, but I figured I'd show it to you. So let's say we've got 6 carbons with p orbitals. We've got 1, 2, 3, 4, 5, 6. The lowest energy one would be where they're all overlapping, meaning you don't have any nodes, any flips in phases. And this is very, very stable. You've got all overlap. All of these electrons are communicating with one another. If we go and add a node, we normally add it to the center position. So now we've got the left side all overlapping and the right side all overlapping. We can go up one more, which is really how we normally draw it, as a double, double, double. So you could think of this as being a double bond, this interior one as being a double bond, this one being a double bond. This exists, and then above that we've got 3 nodes where we can add in a 3rd node. So now we've got 2 double bonds and 2 p orbitals out on the ends, and then we can even go up to 4 nodes where we've got double bond in the middle and 2 empty p orbitals on each side, and then 5 nodes is theoretically possible where every p orbital is flipped. So these conjugated systems are really, really unique. This is how our vision works. Our chromophores in the back of our eye are tuned so that we can excite some of these electrons up to a next higher orbital, or the lowest unoccupied molecular orbital. We call that the LUMO in lab. And when you excite an electron up here, you can actually start to rotate a double bond and get it to flip. And so when high energy light comes into our eyeballs, we can actually start to rotate double bonds, and then they relax back down into their double bond configuration. And that tells our brain, hey, you just saw red. Transmits it all through our body, and we can respond to that color. So our eyes work very similar to how these molecular orbitals work. The reactivity for these molecules you guys got to practice with a little bit, but before we jump into reactivity, let's briefly review how we could make these molecules or prepare them. So preparation of dienes is really similar, so this will be a quiz. Let's say I've got this molecule, and I want to make a conjugated diene. What reagents would I need? No light. We've got bromine, which is a leaving group. We're creating a double bond. Yeah, tert-butoxide, I'd say, would be really good. So if we react this with potassium tert-butoxide, is this going to be an E1 or E2? E2, because it's a strong base. So in this case, we've got an E2 reaction, which we saw all the way back in the fall. So we can create this doing normal elimination techniques. We can also start directly from the dihalide. What if we have the dihalide? Now we've got two leaving groups. What do you guys think? A double E2 reaction, right? So in this example, we can just take tert-butoxide, have excess because we need two equivalents of tert-butoxide, and we can get our double E2 product. So really, the simplest way to make these conjugated systems is just make them through elimination reactions. Luckily, that's the only way we've seen of making double bonds, so we're going to call it good at this step right now. Where these really get interesting is how they react. So making them is kind of trivial. How they react is very, very unique. So let's actually jump back to our problem of the day and see if we can kind of make sense of what's going on with the reactivity of these molecules. So in the problem of the day, I gave you a few examples I wanted you to think about at home. And I tried to give you some hints because the reactivity of these is very similar to the reactivity we've seen in other molecules in the past. So we've got a double bond which can act like a nucleophile or electrophile. Nucleophile, right? Pi bonds can act as nucleophiles. We've got this hydrobromic acid over here which has a net dipole. That means that hydrogen has a partial positive, so our nucleophile wants to attack it. So let's go through and try to come up with some sort of plausible mechanism. So if we grab that proton and kick off that bromine, we've got a couple of options. I could form my carbocation down here, or I could form my carbocation up here. Which one's going to be more stable? Left or the right? I'm hearing two answers. They're both secondary, right? So if we look at this one, it's got two alpha groups on it, it's secondary. If we look at this one, it's got two alpha groups on it, it's secondary. But there's something else going on. Resonance, right? So if we look at this one down here, we can actually show a resonance structure where this pi bond can hop down. And when we do that, we delocalize that positive charge onto a different carbon atom. So this resonance structure is delocalized. Is the one on the right delocalized? So resonance, if we think about resonance, is it a reaction?
No.
No, it's just a state of being for the molecule. So if we think about this molecule on the left, it's not that it's one or the other, it's a hybrid of the two. If we think about this one, we could do a reaction and get a methyl shift,
Yeah.
but resonance would trump any sort of reaction because this one, if we think about it, this carbon has a half charge, and then this carbon has a half charge. This is very, very stabilized. Yep.
I was just about to ask that too. So, I know resonance beats out the rearrangement.
Mhm.
You said that breakthrough still happens regardless. It's a pretty fast reaction as well.
This is a very fast reaction.
I understand the resonance is faster, but wouldn't the shift still happen theoretically?
Theoretically and experimentally, yes. Oftentimes you'll get a mixture out of these reactions, and we'll talk more about that during this portion of the chapter. So let's say that, all right, we've identified our most stable carbocation, which we said was the one on the left. So if we've still got bromine or bromide floating around, we can get two different products out. We can say, all right, this bromine or bromide can attack that carbocation, or it can attack that carbocation. And if we do this, we get two different products out. Oop, sorry. We can get the bromine installed over here, or we can get the bromine installed over here. And one thing I'm going to do is I'm going to draw the hydrogen that was added as blue hydrogen. So if we think about the first one, we installed a blue hydrogen here, and we installed a blue hydrogen here. If we notice the orientation, so in the first step, so you see this blue proton, this corresponds to this proton up here. So we're installing it here. If we look at this one, this bromine is 2 carbons away, right? So this is a 1-2 addition. If we look down here, it installs 1, 2, 3, 4.
Why don't you count the other way?
Yeah.
Why do you have to count that way?
We'll see in other examples, this is a named reaction. This is called 1-2 addition and 1-4 addition. It's not always going to be in a cyclic system, though, and we'll see this in other examples. So they're completely different products. The question is, which one's more stable, the top one or the bottom one?
Actually, the top one.
Say the top one.
So if we look at the top one, really the only difference is where the alkene is, right? Which alkene is more stable, the top or the bottom?
They're the same.
So they're both tri-substituted. They're about the same stability. Which one do you think will have an easier time having the bromine attack?
Yeah.
Top one. And we'll talk a little bit more about this, but if you think about it, the proton was just installed here. That means the bromide ion is going to be really, really close to this carbocation. It's going to have a harder time moving all the way around to the other side of the molecule, to the other carbocation. So now we can think about which product do you think will be more likely?
Top one.
The top one. So the top one will be more likely because the bromide ion will be in very close proximity to that carbocation. But we'll talk more about this and how we can predict each of these products forming.
So will you mark us wrong if we put both and not one of them? Well, both
No,
products?
I'd actually prefer that you draw both products.
Okay.
Yeah. So there are actually 2 more products on there.
Yeah.
Let's skip that for now and go to the next problem so we can see another example of that. All right, so the first step in this one will be our nucleophile grabbing our proton, right? So we can have this grab that proton there, kick off our bromine. And then if we do this, we always want to form our most stable carbocation. So I'm going to leave this bottom one here, and I'm going to draw the proton that added in as blue. So now we've got a carbocation in this position. Does that look good? Is there anything special about this carbocation? It's resonance delocalized, right? So we can say Well, it's not just that carbocation. We also have another one where there's a carbocation over here. So both of these are representations of the same molecule. In reality, it's a hybrid between the two. And now we can say, okay, we've got the bromide around. The bromide's going to be much closer to the top carbocation than the bottom. But let's consider both options and say, okay, this bromide ion can attack that carbocation there, or it can attack that carbocation here. Here's where the story gets a little bit tricky. So we've got Br, and let me draw in our proton. And then we've got a double bond down here. So this is called our 1,2 addition product because the bromine was installed 1 carbon away. And then with the other one, we've now got our bromine 4 carbons away. Oh, forgot my double bond in there. Now we have to ask ourselves, which one's more stable, the top or the bottom?
It's a matter of kinetics versus thermodynamics.
That's very astute, Karen. All right, let's take a look at the alkenes, though. Which is the more stable alkene?
Bottom.
Bottom what?
Tetra.
It's tetra substituted versus di substituted. So if we think about the overall stability of the molecule, this one's the more stable molecule. Which one is the bromide ion closer to attacking, though? Top one, right? Because it gave its proton to this carbon, it's going to be in very close proximity to that carbocation. So kinetically, this is very accessible. It would have to find this other carbocation, which is further away, which makes this kinetically less accessible. But we also have to consider stability. So we're running into this problem of what's going to win? Is it going to be kinetics or thermodynamics? And we're going to talk a little bit of how we can control that. Does anybody remember, though, what technique we use to control kinetics versus thermodynamics? Temperature, right? So if we want to get to the more stable product, do we need high or low? Anybody remember? High, right? What if we want to get to the kinetic product? Low temperature. So we can actually control this reaction a little bit more. All right, so let's jump back to our lecture notes and.
Professor, I have one question before you.
Yep.
So you do the very first step, and you form your carbocation there. Couldn't you? I mean, you have the proton added there. Could you also have the proton added at that more substituted side? And wouldn't that have been?
So you're saying why didn't we add the proton in this tertiary position? Because then we'd form a primary carbocation that's not even stabilized with resonance. So that'd be very, very unfavoring. This one, we're forming a tertiary carbocation that is stabilized by resonance. So this will really be all that you'll get. That one would be very unfavored. Yep.
Also, weren't those atomers?
Yeah, we'll get into considering whether or not it will be racemic. But if we look at this one, we're going through a trigonal planar transition state, so it can attack from the top face or bottom face. So you get a racemic mixture of this. What about this one? There's no stereocenter, so this one we wouldn't get into racemic mixture. So good question. Yep.
So is carbocation stability or alkene stability more important?
So it depends on what we're looking at. If we're looking at kinetics, oftentimes stability of your transition state is more important. If you're looking at thermodynamics, you're just looking at the final product and asking which is more stable. I don't care how you got there, which one's more stable. Yeah. Okay, so let's jump back into our lecture notes and take a look at what's going on here with just a really basic system. So I've got my classic diene example here. Chemists like to make jokes about dienes a lot too because it sounds like you're dying, but I'll let you guys play around with that. Yeah, cheesy chemistry jokes are the best. So first step, our nucleophile will attack our proton just like we saw in the other examples. Kick off our bromide. And when we do this, we said we prefer to form the more stable carbocation. So in this case, it's a carbocation that is resonance stabilized. Does anybody remember what this functional group is called, where you've got a cation on a carbon next to a double bond? Yeah, it's an allylic carbocation. Carbocation. And these are very, very stable because of that resonance delocalization. And we said, okay, if you've got your Br minus or your bromide around, that it can add into either of these positions. So it can add into this side, or it can add into this side. And when we do this, we get two different products. And on this one, we've got our bromine attached onto the end. And I'm drawing in our protons again. So now if we consider the positioning of our protons, we can say, all right, the proton was added in position 1 on each of these. Our bromine on the right one was added into 2, 3, 4. So this is called our 1,4 addition product. If we look at the one on the left, we can still count out to 4, but our bromine added onto the 2 position. This is 1,2 addition.
You do the counting, you only count on the side where added.
Yeah, it's relative to one another, so 1,2 just means it's adjacent. 1,4 means that you've got a separation of additional carbons in there. So kind of like 1,3 diaxial interactions, it's just relative to one another. Okay, and then let's take a look at the various products here, because this is a nice, simple example. Which alkene is more stable, the one on the left or the right?
Right.
The one on the right is more stable, and that's because it's di-substituted. So we'll say more stable / thermodynamic. Product. The one on the left, that 1,2 addition product that we're looking at, we said that we protonated in that one position. That bromide ion is going to be really, really close to the resulting carbocation, so this one's more accessible. So we said that this would be our kinetic product, right? So we'll call this our more accessible kinetic product. So if we're trying to get 1,2 addition, do we need high heat or low heat? Exactly. It's favored under lower temperatures. At lower temps. And then if we look at our 1,4 addition product, if we want to try to favor its formation, we just crank the heat up, right? So if we're running this in our variac, we just turn the dial up. To be favored at higher temps. Does that make sense?
So is it fair to say that the lower temps is more accessible and at higher temps it's usually more stable?
At higher temps, you're always going to get your thermodynamic product. At lower temps, you can occasionally intercept your kinetic product. Let's actually look at an energy map of this, and maybe it'll make a little bit more sense that way.
Can you wait?
Oop, yeah.
When you name it the 1,2 addition, you don't take the name of the actual molecule. Like, you're not taking into consideration.
No, I'm not trying to name the resulting product. I'm just calling the addition 1,2 because the proton is on carbon 1, the bromine's on carbon 2.
You can start from either.
You could do it from either side. It just depends on where that proton was first added. You'll name that carbon 1.
Okay.
Yeah. This doesn't have to do with IUPAC naming, just the relative position of that proton in the bromine.
All right.
Yep. All right, so let's take a look at the energy profile that's going on here. So we've got energy on one axis, and we've got our reaction coordinate on the other. In both cases, we have the same starting material, so it will have a fixed energy. And let's do an example where we're doing the 1,4 addition. So we said with 1,4 addition, we're forming the more stable product, so its position should be lower than our blue 1,3 addition, or 1,2 addition. So let's label these. 1,2 addition. And then red will be it'll be 1,4 addition. And we said that with 1,4 addition, it's more stable, but it has to have reorganization. That bromide has to go around to a different side of the molecule. That takes energy, so it's going to have to go more uphill. If we look at the 1,2 addition, that bromide doesn't have to go very far. It doesn't take as much energy to get it onto the other side of the molecule because it's in close proximity. So it's got a little hump, and then it forms the less stable product. So at lower temperatures, we have enough energy to overcome this blue hump, and it gets stuck at a less stable product. At higher temperatures, yeah, it can overcome the blue hump, but it can even go backwards and ultimately go over this big red hump and then get stuck in what's called a thermodynamic sink. So you can think about this blue reaction. We don't have a very big difference in energy, so even if we did form the product, it's in equilibrium and could go backwards. But then some of it will get stuck over on this red side and get stuck in this energetic sinkhole. Has a hard time getting out of because this delta G value is much, much greater. Does that make sense? You can almost think about it like a roller coaster. How much energy does it take to get over that hump? It takes a lot less energy or a lot less heat to get over this blue hump, so we get our thermodynamic product. It takes a lot more energy to get over this red hump, and that's our thermodynamic product. All right, let's do a couple examples before we take off today. So let's take this example, and in particular, let's use hydrobromic acid. And I'm going to run it cold, so at 0 degrees Celsius. We'll run this in an ice bath. I want you guys to try to come up with a reaction mechanism. But before you begin, do you guys think this will be the thermodynamic or kinetic product? Kinetic, because we're at low temperature. So should it be 1,2 or 1,4? Probably 1,2. This is 0 degrees Celsius, so if I'm trying to designate temperature, I'll oftentimes include that. You guys think it matters which alkene we use as our nucleophile?
No,
Because it's symmetric, right? This is in the same chemical environment as this alkene, so it doesn't matter which one you use. All right, let's try to go through this now that you guys have had a chance to get it started. The first step will be our nucleophilic attack of that proton. which will give us our tertiary carbocation. But am I done?
No.
Nope. We need to have our resonance structure where that carbocation is delocalized. And it could be here. So let's go through and label that proton that we added in as blue, just so we can keep track of it. And we'll box this in to show that it's resonance delocalized. Oh. Ah, shoot, wrong pen color. All right. Now we've got to ask ourselves which product will be more likely. So we've got Br minus that can add into either of these. So it could add into this carbocation, or it can add into that carbocation. So let's draw both products out. And let me finish in by drawing where our original proton was added in. So which product will be favored, the one on the left or the one on the right?
The left.
Left, exactly, because we're running it at lower temperature. This one will be favored, meaning it's going to be our major product. And then the one on the right will be our minor product. If we wanted to get the one on the right instead of the one on the left, we could have cranked up the heat, really baked this thing, and then we could favor the one on the right rather than the one on the left. Yep?
Is there like a specific temperature where you only observe one or the other?
Oftentimes you'll observe some sort of ratio. Sorry, that green's a little hard to see. So it may be 90% this, 10% this, and then when you crank up the heat, you can get up to 90% this, 10% this. It's very hard to get it to go exclusively to one product over the other. You normally end up with some sort of mixture. All right, so try to work on the next problem of the day by tomorrow, and then we'll talk a little bit more about thermodynamics versus kinetics, and then we'll start getting into pericyclic reactions too.
Another great lecture.